In mathematics, a volume form on a differentiable manifold is a nowhere-vanishing top-dimensional form. Thus on a manifold M of dimension n, a volume form is an n-form, a section of the line bundle omega n equals lambda n, that is nowhere equal to 0. A manifold has a volume form if and only if it is orientable. An orientable manifold has infinitely many volume forms, since multiplying a volume form by a non-vanishing function yields another volume form. On non-orientable manifolds, one may instead define the weaker notion of a density. A volume form provides a means to define the integral of a function on a differentiable manifold. In other words, a volume form gives rise to a measure with respect to which functions can be integrated by the appropriate Lebesgue integral. The absolute value of a volume form is a volume element, which is also known variously as a twisted volume form or pseudo-volume form. It also defines a measure, but exists on any differentiable manifold, orientable or not. Kähler manifolds, being complex manifolds, are naturally oriented, and so possess a volume form. More generally, the nth exterior power of the symplectic form on a symplectic manifold is a volume form. Many classes of manifolds have canonical volume forms. They have extra structure which allows the choice of a preferred volume form. Oriented Riemannian manifolds and pseudo-Riemannian manifolds have an associated canonical volume form. Orientation. A manifold is orientable if it has a coordinate atlas all of whose transition functions have positive Jacobian determinants. A selection of a maximal such atlas is an orientation on M. A volume form omega on M gives rise to an orientation in a natural way as the atlas of coordinate charts on M that send omega to a positive multiple of the Euclidean volume form. A volume form also allows for the specification of a preferred class of frames on M. Call a basis of tangent vectors right-handed if the collection of all right-handed frames is acted upon by the group GL plus a general linear mappings in n dimensions with positive determinant. They form a principal GL plus subbundle of the linear frame bundle of M, and so the orientation associated to a volume form gives a canonical reduction of the frame bundle of M to a subbundle with structure group GL plus. That is to say that a volume form gives rise to GL plus structure on M. More reduction is clearly possible by considering frames that have thus a volume form gives rise to an SL structure as well. Conversely, given an SL structure, one can recover a volume form by imposing for the special linear frames and then solving for the required n-form omega by requiring homogeneity in its arguments. A manifold is orientable if and only if it has a volume form. Indeed, SL-GL plus is a deformation retract since GL plus equals SL times R plus, where the positive rails are embedded as scalar matrices. Thus every GL plus structure is reducible to an SL structure, and GL plus structures coincide with orientations on M. More concretely, triviality of the determinant bundle is equivalent to orientability, and a line bundle is trivial if and only if it has a nowhere-vanishing section. Thus the existence of a volume form is equivalent to orientability. Relation to measures. Given a volume form omega on an oriented manifold, the density, omega, is a volume pseudo-form on the non-oriented manifold obtained by forgetting the orientation. Densities may also be defined more generally on non-orientable manifolds. Any volume pseudo-form omega defines a measure on the Borel sets by the difference is that while a measure can be integrated over a subset, a volume form can only be integrated over an oriented cell. In single-variable calculus, writing considers as a volume form, not simply a measure, and indicates integrate over the cell with the opposite orientation, sometimes denoted. Further, general measures need not be continuous or smooth. They need not be defined by a volume form, or more formally, their Radon-Nikodym derivative with respect to a given volume form need not be absolutely continuous. Divergence. Given a volume form omega on M, one can define the divergence of a vector field X as the unique scalar-valued function, denoted by divx, satisfying where Lux denotes the Lie derivative along X. If X is a compactly supported vector field and M is a manifold with boundary, then Stokes' theorem implies, which is a generalization of the divergence theorem, the solenoidal vector fields are those with divx equals 0. It follows from the definition of the Lie derivative that the volume form is preserved under the flow of a solenoidal vector field. Thus solenoidal vector fields are precisely those that have volume-preserving flows. This fact is well known, for instance, in fluid mechanics where the divergence of a velocity field measures the compressibility of a fluid, which in turn represents the extent to which volume is preserved along flows of the fluid. Special cases. Lie groups. For any Lie group, a natural volume form may be defined by translation. That is, if omega E is an element of, then a left invariant form may be defined by where LG is left translation. As a corollary, every Lie group is orientable. This volume form is unique up to a scalar, and the corresponding measure is known as the Haar measure. Symplectic manifolds. Any symplectic manifold has a natural volume form. If M is a 2n-dimensional manifold with symplectic form omega, then omega n is nowhere zero as a consequence of the non-degeneracy of the symplectic form. As a corollary, any symplectic manifold is orientable. If the manifold is both symplectic and Riemannian, then the two volume forms agree. If the manifold is Kähler Riemannian volume form, any oriented pseudo-Riemannian manifold has a natural volume form. In local coordinates, it can be expressed as where the other one forms, providing an oriented basis for the cotangent bundle of the n-dimensional manifold. Here is the absolute value of the determinant of the matrix representation of the metric tensor on the manifold. The volume form is denoted variously by here. D is the Hodge dual. Thus the last form emphasizes that the volume form is the Hodge dual of the constant map on the manifold, which equals the Levi sub eta tensor epsilon. Although the Greek letter omega is frequently used to denote the volume form, this notation is hardly universal. The symbol omega often carries many other meanings in differential geometry. Thus, the appearance of omega in a formula does not necessarily mean that it is the volume form. Invariance of a volume form. Volume forms are not unique, they form a tensor over non-vanishing functions on the manifold, as follows. Given a non-vanishing function f on M, and a volume form is a volume form on M. Conversely, given two volume forms, their ratio is a non-vanishing function. In coordinates, they are both simply a non-zero function times Lebesgue measure, and their ratio is the ratio of the functions, which is independent a choice of coordinates. Intrinsically, it is the Radon-Nikodym derivative of with respect to. On an oriented manifold, the proportionality of any two volume forms can be thought of as a geometric form of the Radon-Nikodym theorem. No local structure. A volume form on a manifold has no local structure in the sense that it is not possible on small open sets to distinguish between the given volume form and the volume form on Euclidean space. That is, for every point P in M, there is an open neighborhood U of P and a diffeomorphism phi of U onto an open set in Rn such that the volume form on U is the pullback of along phi. As a corollary, if M and N are two manifolds, each with volume forms, then for any points, there are open neighborhoods U of M and V of N and a map such that the volume form on N restricted to the neighborhood V pulls back to volume form on M restricted to the neighborhood U. In one dimension, one can prove it thus. Given a volume form on defined N, the standard Lebesgue measure pulls back to under F. Concretely, in higher dimensions, given any point, it has a neighborhood locally homeomorphic to, and one can apply the same procedure. Global structure. Volume. A volume form on a connected manifold M has a single global invariant, namely the volume. which is invariant under volume form preserving maps. This may be infinite, such as for Lebesgue measure on a disconnected manifold. The volume of each connected component is the invariant. In symbols, if is a homeomorphism of manifolds that pulls back to, then and the manifolds have the same volume. Volume forms can also be pulled back under covering maps, in which case they multiply volume by the cardinality of the fiber. In the case of an infinite sheeted cover, a volume form on a finite volume manifold pulls back to a volume form on an infinite volume manifold.